Hello everyone, welcome back to 360DigiTMG's second day of domain analytics session. In the last class, we were discussing about the applications of machine learning in healthcare analytics. In last class, we are discussing about the application, where exactly we can apply the machine learning when it comes to healthcare analytics. Like classification, we have discussed. We can apply the machine learning when it comes to classification and clusters. We can apply machine learning to do predictions. And we can also apply the machine learning when it comes to automation and ranking as well. So we have discussed all this. How can we apply the machine learning in this all? When it comes to classification, to decide whether that particular person has any anomaly in his health, or does that particular person has any cancer or not. In cluster, how do we segregate patients based on their health condition? That we have seen in the previous session. In this session, we'll look into how, when we are working on a data science project, that is in healthcare analytics. In healthcare, it's not just for healthcare. It could be any industry. The process or the project that we are doing in our data science will be same. That is, we have discussed as a CRISP-ML, cross industry standard process, whether it is healthcare analytics or any other any industry. That could be agriculture, that could be HR, accounts, cyber, law, everything. For everything, we will be using the CRISP-ML methodology that we have discussed in the last session. And we have also discussed what are the stages of analytics. And we have gone through what are the phases we'll be having when it comes to CRISP-ML. And we have also discussed what is the inferential statistics. Like, we'll be having population. So it is not possible to take all the reviews of the population. In that case, what we are doing? Simply taking the sample out of this population, and we are making the comments on the population. Whatever the inferences we are getting on sample, the same we are applying on the population. That is called inferential statistics. In this session, we will be discussing about what are the models we'll be having. What happens when the data is given and the labels are not given? When it comes to data, we'll be having two types. In one data, we won't be having any labels. In some data, we'll be having the labels. Let's say if you want to segregate a patients based on their health condition. In that case, you don't need any labels. Based on the different condition, you can simply segregate into different categories. But when it comes to whether that particular person has any whether it is cancer, whether it is diabetes, whether it is heart disease, if he has that particular illness, you want to predict. In that case, you need labels. So based on this data, we'll be categorizing model into two types. The machine learning models are two types. These are the phases when it comes to any data science project. In that, we'll be having business understanding, that is business understanding or data understanding. That is the very first phase you have to go through. Then you have to prepare the data. And then we will be doing the model building and model deployment, model evaluation and model deployment. In the end, we will be having monitoring and maintenance. That is it also. This one also we have discussed in the previous class, and we have also discussed that CRISP DM. Previously, it is called as a CRISP DM. In that, we won't be having monitoring and maintenance, but CRISP ML. When it comes to CRISP MLQ, the monitoring and maintenance has been added. Yeah, when it comes to supervised and unsupervised, based on the data, the models are categorized into one, supervised, and next is unsupervised. These are the two types of models we'll be having. What happens in unsupervised? We won't be having any labels. Like I explained earlier, we won't be having any labels in our data. In that case, we have to go for segregation or clustering. In unsupervised, we have different models like clustering, association rules, networking, or network analytics, recommendation engine. These are all the algorithms comes under unsupervised learning. Unsupervised learning. What happens in our unsupervised? We won't be having any label in our data. Whatever the data frame that we have been provided, in that we won't be having any label. So these are the different algorithms we'll be using when it comes to unsupervised learning. And one more, we have supervised. In that case, we will be provided with labels. Label means that is output. We know the output of that particular data. So what will be the output that we know? Based on that, we'll be training the model. All of the historical data that has label, we'll be training the model based on that. And then we are supplying the new data in order to do predictions. Yeah. When it comes to unsupervised learning, there is a process that we have to follow. And when it comes to supervised learning, there is also one more process you have to follow in order to build the model, or in order to find out the pattern, or in order to find out the predictions. When it comes to supervised, you will be having historical data. See, whenever we are talking about the machine learning models, we will be having the historical data. Based on the historical data only, we will be training that particular model, and we are supplying the new data in order to do the prediction. Even when it comes to unsupervised learning, we'll be having the historical data, but without any labels or without any output columns. So what we will do once we have a historical data, we have to clean that data. And then we supply to model. And we form rules or patterns. Patterns are rules. See, data itself has some patterns. That could be data having the labels or data having without labels. It will be having some patterns. That patterns only machine learning will learn, and it comes up with some rules. It come up with some rules and pattern, and then if you supply the new data, it will segregate based on the the pattern that machine learning learned. Based on that, it will do the segregation, or it will do the prediction. Yeah, when it comes to supervised, we have completely a bit different process that we have to follow. The very first time, whenever you are having the data, you should see whether you have labels or not. When you have labels, then only you can do the supervised learning. Once you have the label, you have to go through pre-processing, of course. See, whenever we are getting the data from the outside, it won't be perfect. We have to go through some pre-processing techniques in order to clean the data. You might be having some missing values. You might be having duplicate values. You might be having categorical values. What happens? Machine learning won't take the supervised model won't take categorical values. You need to do encoding. So you have to go through all those pre-processing techniques. Then only you can take the data and do the predictions. When it comes to supervised, so we'll be having data, we'll be applying. So whatever the data you'll be having, that we will split into train and test. We'll be splitting the data into train and test. And based on training data, whatever the data that we have split, let's say you have 100. Let's say you have 100 data sets. In that, I'm splitting into training and testing. It completely depends on the data frame size you will be having. So most of the time we'll be doing 80-20 ratio. But it is completely depends on your data frame. If you have 100K, if you have 100K entries, in that case, you can go for 99% training, or 90% training and 10% testing. It's completely depends on you, or depends on the data frame, the size of the data frame you will be having. Why we are splitting into 80-20%? So that whatever the pattern that we have in the 80% of the data, most of the pattern that can also present in the test data. That is why we'll be splitting into 80-20% ratio. Once it is done, we will be training the machine learning based on the trained data. We'll be training the model based on the trained data. And once the machine learning is trained, then you can supply your test data. Then you can supply your test data, and then you can do the prediction. Here we have one more thing called as a validation data. Here we have one more thing called as a validation data. Let's say it is data. It is the training data. Validation and testing. So why do we need the validation data? So whenever you are working on the model that has so many hyperparameters, in that case, you have to tune your model. Whatever the model that you have built, you have to tune. Once you have trained the data on training data set, then you have to supply your validation set in order to tune the model. But if you don't have any much parameters that are much hyper parameters, you can simply go for training and testing. But if you have parameters are very high for your model, in that case, you can go for validation split as well. In that case, you can simply split 60-20-20 ratio. It is not a thumb rule, but it is completely depends on your data frame size. It will vary. So whenever you have a high hyperparameter, when you have more hyperparameters, in that case, you can use the validation set and you can train the data. Once you have trained, supply the validation and tune your parameters and check your accuracy. All the hyperparameters, you have to keep, I mean, it is kind of circle. First train your model, then supply your validation data, tune your model and check the accuracy. Again, train your model, supply your validation data, change your hyperparameters and check your accuracy. Once you are getting good accuracy, see, we have already have a validation data. Then why we are going for testing data again? In this process, whenever you are training your, whenever you are doing the hyperparameter tuning, in that case, there is a possibility of leakage of data. What happens when there is a leakage of data? So it will completely, whatever the model that you are building, it will completely learn the pattern. It doesn't use any logic. It will simply copy as it is. It will copy the validation set. In that case, there is a possibility of getting high accuracy. Sometimes you will get 100% accuracy. In machine learning models, it is very rare. You won't be getting this much of accuracy. Barely you will get like 90 to 95%. It is also completely based on the data set you are using. So in order to avoid that leakage, we have to test on the testing data. Once you have come up with like good accuracy, then test using the testing data. In that case, you will come to know like whatever the accuracy you are getting, is it exact accuracy or it is a bias accuracy, or it is just whether that particular machine learning model, whatever you are training, whether it is learning or it is simply copy pasting. That you'll come to know once you do the, when you supply the testing data set. So this is all about how do you split the data. Whenever you have this data set, how do you split the data? When you have small parameter, just 1, 2, in that case, you can do manual iterations, right? When you have a high parameters like machine, the decision tree or XGBoost, in that case, you can go for validation set. When you have high parameters, then you can split into train, test, or validation, and then test. Anything. So this is how you will be splitting the data frame. So this is the process how you do split the data frame, the whole data frame. It is you are splitting into training, and then you are splitting into validation, and then testing. What happens here? When you have a hyperparameters, you will do whatever the model that you are considering or algorithm. You will be training that model, and then you will be supplying the validation data set to that. If you are getting good accuracy, then you can go for testing. If it is not, do the hyperparameter tunings. It is complete one cycle. It will keep happening until you are getting the good accuracy. Once you got the good accuracy, then supply your testing data. In that case, you can confirm that whatever the accuracy you are getting in validation, it is nearly true. Then you can go with testing, and then you can whatever the machine learning model that you are building, you can go for deployment. Once you are getting the testing accuracy is good, then you can go for deployment. If you are not getting any good accuracy, in that case, maybe you haven't added the features. What are features? Those are inputs that we are using for machine learning. Those are also called as independent variables or input columns or features. So whatever the feature that you are taken, maybe not satisfying the output. Maybe they're not influencing the output. Maybe it is not useful for the prediction of the particular output. You can go back and you can research and you can add the feature which are necessary to that particular prediction. So yeah, once the model building is done, then what you will do? You have to go for evaluation. So whether it is classification, whether it is regression, what is classification, guys? So whenever the data or label that will be having, whatever the label you have, label means output. In supervised only I'm talking about. When it comes to unsupervised, we won't be having any labels. So it is completely different case. But when you have labels, if those labels or outputs are continuous, if those outputs are continuous, that are like 25 by something in decimal form, in that case, it is called as a, we'll be going for regression. When the output column, whatever the output column may be having, or label column is in continuous form, in that case, we will go for regression models. But whenever our output or label column is in discrete form or categorical form, let's say in that case, you will be going for classification. Let's take an example for this. See, when you, let's say, based on the inputs or features, you want to predict the salary of that particular some person. Yeah, it won't be applied in healthcare analytics. When it comes to, see, we'll be having one use case predicting the adipose tissue. Predicting the adipose tissue based on the circumference of, body circumference, you will be calculating the adipose tissue. That we have one use case, we'll learn. In that case, the output will be continuous. Adipose tissue output will be continuous. In that case, you have to go for regression. When the output column or label column is in continuous form, then we will be going for regression. In the same case, when it comes to classification, let's say whether that particular person has diabetes or not. In that case, what could be our output? Yes or no. These are our prediction or classes. In that case, we should go for classification. Whenever our output is in the form of discrete means 0 or 1, or categorical, that is yes or no. In that case, we should go for classification. When output is in regression, the continuous, something 30.5 or any value 30,500 by 5 rupees, something like that. In that case, you will be going for regression. So that is our about regression and classification. We'll be having, see, when it comes to classification, we won't be having just two. When you have more than two classes, whatever the categories we'll be having. And when it comes to diabetes, yes or no. Based on the historical data, you will be predicting whether that particular person has a diabetes or not. Here it is just two classes. In that case, it is called as a binary classification. But when you have more than two cases, what happens? When you have more than two cases, there could be, right, if you want to predict whether that particular person is in which stage of cancer. So in that case, you will be having different outputs, right? First stage, second, third, fourth, or something like that. In that case, we will be having more than two cases. That is called as a multi-class classification. Multi-class classification. And when it comes to regression, anyway, you will be having different outputs. So we don't even have anything like multi-class regression or binary regression. So whatever the outputs you are getting, all are unique one. In regression, the outputs are all are unique only. So unique only. In that case, you won't be having anything like that. But when it comes to classification, we'll be having like binary classification and multi-class classification. When you have just two classes in your output or in a label, it is called as a binary classification. When you have more than two, in that case, it is called as a multi-class classification. So once the building is done, whatever the model that you have built, but you have to check. Now we have to check whatever the accuracy you are getting, whether is exact accuracy or not. You have to evaluate. You have to evaluate the model. Evaluating the model. So we have different process when it comes to classification. We have some completely different, and when it comes to regression, we have different process. When it comes to classification, we have something like confusion matrix. We have confusion matrix when it comes to classification. So what is confusion matrix? So it is a matrix of true positive, false positive, false negative, and true negative. What are those? I'll explain. So what happens whenever you are making the predictions? Prediction means what? Based on historical data, you have trained your machine learning and you have supplying the new data and you are predicting the output. But whenever you are building model, we'll be having outputs. From that only we are data frames. From that only we are splitting into train and test, right? From that only we are splitting into train and test. In train and test, in both cases we'll be having output. In both we'll be having output. But when it comes to test, when we are applying, we'll be having predictions as when we are supplying the test data. In that case, we will be getting predictions, right? Whatever the prediction we are getting right after supplying to the model, whatever the model that we have built, when we are supplying the test data set, we will be getting some predictions. We will be comparing the whatever the prediction that we have got with existing outputs. So train and test will be having output. Hence, it is called as a supervised, right? Labeled data. So we'll be having outputs, and then whatever the outputs, prediction that we have got, we have to compare both. Then only we can say, right, whatever the historical data we are having, those are real. Those are real outputs. And whatever the prediction that we are doing, it is done by the machine learning machine that we have trained that did the prediction. So in order to check the accuracy, we have to compare both the real-time outputs and the predicted output. We have to compare those. Based on that only, we will be deciding the accuracy of the particular model. Based on comparison, based on that only, we will be deciding the accuracy of the classification. Accuracy of the classification. How are we going to do that? We'll see. Let's say it is real, I mean whatever the data frame contain the previous, or whatever the data frame outputs we have, those are real outputs and these are predicted. We are predicting about COVID. We are predicting the COVID. Real, you have a COVID. In real, you have a COVID. You went to one diagnostic center to check. Or you can say, whatever the data frame we have is about all the COVID cases. You went and you have given your inputs and the prediction came out. You have COVID, but it is predicting like you don't have COVID, no COVID. In that case, what happens? It is a false negative. You have a COVID, but it is predicting you don't have a COVID. It is a false negative case. When you have no COVID, but it is predicting as a COVID, in that case, it is called as false positive. When you don't have a COVID, but it is saying it is a COVID, you have a COVID. In that case, what it is called? False positive. You have a COVID and it is predicting that you have a COVID. In that case, it is called true positive. True positive. When you don't have a COVID and it is predicting as you don't have. In that case, it is called as true negative. So when you have a COVID, but it is not, it is predicting as you don't have. In that case, it is false. Prediction is false. False negative. You don't have, but it is predicting as you have. In that case, it is false positive. If you have COVID, but it is it is also predicting that you have COVID. In that case, true positive. You don't have COVID, and the prediction is also came out to be true. In that case, true negative. So this is the prediction. This is how we compare the prediction and how we come up with the accuracy. Then we'll come up. The accuracy will be true positive cases plus true negative cases by all. True positive plus true negative plus false positive plus false negative. When you compare all and take those values, with those we can calculate the accuracy of the model. Accuracy of the model that you have built. So one thing you should remember when you are working on the healthcare analytics. Whenever you are working on healthcare analytics, you should be aware of this. Let's say you are working on cancer data. When you are working on the cancer data, false negative cases could be detrimental. What is false negative, guys? You have a cancer, but prediction came out to be no cancer. It is a real case. I mean, he has cancer, but you are predicting that you don't have a cancer. It is called false negative. Whenever you're working on any healthcare analytics or life science project, you should be very careful about false negative. What happens here? He has cancer, but you are saying you are predicting that you don't have a cancer. In that case, what happens? Whoever that particular person is, he get relaxed and he'll get back to his normal life. Maybe you had a opportunity to detect the cancer in the very early stage. But by the time he came to know that he has a cancer, he might be in the last stage. Due to your prediction, there is a life. I mean, you are risking a life just because your prediction gone wrong. So whenever you are working on the healthcare analytics or life sciences, you have to be very careful about it. So accuracy doesn't matter in that case. I mean, accuracy is not completely doesn't matter, but whenever you have a false negative cases, as low as it can be, whenever you bring down these false negative cases, minimal, then only we'll be considering that model. See, it is not like you might be losing something, property. It's not like that, right? It's life. So you won't be, even though you have like false negative cases like 1 or 2, in that case also, whatever the model that you are predicting, whatever the model that you are building is not fit for the deployment. So you have to decrease as much as you can. Even though you have false negative case, when you have false negative case are like 0, and your prediction, your model accuracy is about 75% or 80%. Still, in that case, it is acceptable. But if you are having false negative cases are like 2% of whole data frame, and then you are getting like 90, 93% or 94%. Still, that model, whatever the machine learning model you are building, won't be acceptable, since because you are risking the life of one person. So these are the true positive, true negative. Yeah, true positive is fine, and true negative is also fine. You need to be, you need to get as much as you can. I mean, whatever the positive cases you will be having, among that you have to get as much as you can. But when it comes to false positive, this is also not good thing, but it is not that much dangerous. What happens in false positive? You don't have a cancer, but it came as you have a cancer. When you have already, it came as a cancer, you'll be going for other diagnosis, right? In that case, you might come to know that you don't have a cancer. But once you said like the guy, that particular person don't have a cancer, even though he has a cancer. In that case, he won't be going for any other tests. So he will simply relax. So you should be very careful about the false negative cases. So that is accuracy. And if you want to calculate, you can simply say 1 minus accuracy is equal to error rate. Accuracy will be 100%, right, normally. So whatever the accuracy you are getting, whether it is 90% or something like that, you can simply subtract from 1, you will be getting the error rate of that particular model. This is for classification. How we going to evaluate our model? This is for classification. So in that we have something like so we'll be having, whenever you have a classes, different classes, class A, or whether it is true. Class means whatever the values you have in output column or label, yes or no. These are one class. This is one class and this is class. Binary classification. That is why we'll be calling, when you have just 2 class, binary classification. But whenever you are going for model building, you should consider that whether all the classes, yes or no, are balanced or not. See, when you have just 90% of the cases are yes, and you have just 10% of cases are no. In that case, it might create biased result. Most of the time, you will be having yes back patterns only, pattern that is related to yes, but you won't be getting no patterns. Machine learning won't be able to learn these patterns. To avoid that, we have to make sure that whatever the data frame that we are taking, whatever the data set we are taking, it should be balanced. It should be balanced. Then only we can go ahead. Or if you didn't check for the balanced data, then you have to go for precision, sensitivity, specificity, and F1 score. What is precision? So whatever the values that you have, probability of correctly identifying a random patient with a disease having a disease. You are simply taking one random person and you are predicting that particular person has a disease, and you are predicting same. Whatever the prediction you are doing and the person has the same, in that case we'll be calling as a precision. You are predicting the random person's disease, and it came as true positive, you can say. True positive. It is called precision. That is the formula for precision. True positive by true positive plus false positive. Sensitivity. So whatever the positive cases you have in your data frame, among that, how many you have predicted same. Whatever the positive cases you have in your data frame, among that, how many you predicted the positive. That is first sensitivity. And when it comes to specificity, that is true negative cases. Among the true negative, negative cases, how many you have predicted as a true negative. That is a specificity. Sometimes you would it is very hard to balance this precision and specificity. It is very hard to balance because when you increase one, that decreases. So that what we'll do, we'll simply balance both precision and recall. We'll be balancing the precision and recall. That is called F1 score. When you don't know how to balance them, you can simply go for F1 score. F1 is equal to 2 into precision into recall by precision plus recall. So that is the when you have unbalanced cases. When you have unbalanced cases, don't simply depend on the accuracy that you are getting. So when you have unbalanced data, even though you are getting 90% accuracy, it is completely biased accuracy. You don't even have you have 90% S cases, S class, and you don't have not even 10% of no class. In that case, most of the pattern that you are training to the model, it is completely S class only. So whenever the model is taking random values, possibility of getting S will be very high. In that case, it results in a biased output. In that case, even though you are getting 90 or 95% accuracy, it is invalid accuracy. So you have to check for balanced cases, whether you have any balance or not. If you don't have a balanced cases, in that case, we have so many other techniques how to balance the data, like smooth technique, oversampling, undersampling. We have different techniques that you can go through it. Then you can apply then you can go for model building. That is for evaluation metrics for classification. When it comes to regression, we will be having something like mean error, mean absolute error, mean square error, root mean square error. These are all different metrics to evaluate the regression model. What is you can use any one of these. You can use any one of these to check the error rate. So what is error rate? You will be having accuracy plus error rate is equal to 100, right? Let's say it is actual data. It is actual data and you have forecasted it. So what is forecasted? Predicted output, you can say. It is a real, it is a predicted. Whatever the value, whatever the difference we have, it is a real value and you have predicted, there is a difference. Whatever the difference we have, that is called as an error. That is called as error. It is a real value and the prediction that you made using the machine learning model, you got 199. In that case, the error is -1. In that case, we'll be having different entries set. So many entries, not just one entry. So what we have to do? We have to calculate the sum of the all. When you calculate sum of the all, it will become 0. So in that case, you won't be able to calculate the accuracy. In that case, what you have to do? You have to go for mean square error. Mean square error, or you can go for root mean square error. These are all having their own benefits, their own advantages, but most of the time we'll be using the root mean square error. What we'll do? We'll simply square it. We'll simply square the errors and we'll add it. Whatever the value we are getting, we'll try to decrease as much as we can. We are decreasing error rate means we are increasing the accuracy. whatever the error rate we are getting, we will try to decrease as much as we can using the hyperparameter tool. We'll do different iterations. We'll try to decrease the error rate in order to increase the accuracy of the model. This is about the evaluation metrics. Evaluation when it comes to regression. These are also called as error function. We'll be calculating the error of that particular model. In that case, we can call as error functions as well. And one more thing you should be aware when you are working on the data set or even working on the project, you should be aware about overfitting, underfitting. You should be aware about it. See, when you are getting training accuracy is equal to 95% and testing accuracy is about 80%. There must be something wrong, right? When you are, let's take one example. You are working hard. You are working really hard for examination, and you have given your best. When you are working really hard, in that case, you should be getting higher marks. You are prepared, you are prepared very well, and you are expecting at least 90 out of 100, and you got just 35%. There must be something wrong. There is something wrong with your model, right? So in that case, you should be very you should be aware about overfitting and underfitting. What is overfitting and what is underfitting? Let's say training. Once the model is built, we will be looking into training accuracy and testing accuracy. We'll be looking into training accuracy and testing accuracy. We'll be having something validation accuracy as well, but we won't be considering that. We'll be considering only testing accuracy. When you have a small, limited parameters, you can say, high or hyper parameters. So in that case, what happens? Whenever the training accuracy is high and testing accuracy is very low, whenever the training accuracy is very high and testing accuracy is very low, in that case, we'll be calling as overfitting. Now, overfitting. That is also called as a variance. Whenever the training accuracy is very high and testing accuracy is low, in that case, we'll be calling it as overfitting. Same way, whenever you have when training accuracy itself low, in that case, testing accuracy will be low only. Whenever training accuracy is low, testing accuracy is obviously low. In that case, it is called as an underfitting. Yeah, it is underfitting. That is also called as a bias. When you have a training accuracy is high and the testing accuracy is low, in that case, it is called as a overfitting. When training accuracy itself low and testing accuracy is more than that low, in that case, it is called as a underfitting. So how do you avoid this? How do you avoid the overfitting? How do you avoid the underfitting? What is happening in the overfitting? You will be getting good accuracy when it comes to training. It is a good accuracy, high accuracy you are getting, but it is not performing when it comes to testing accuracy. Testing accuracy, model doesn't performing well. In that case, what you can do? You can go for regularizations. You have methods to tune the hyperparameters, and then you can go for regularization techniques in order to avoid this overfitting. Since model is training on training data, model is training well. The accuracy are getting good, but when it comes to testing, it it is performing lower. In that case, you can do some changes, regularization you can do, or you can do some hyperparameter tunings, and you can set the model, or you can increase the accuracy of the test. But when it comes to underfitting, the training accuracy itself is low. In that case, what it is saying, there must be something wrong with your data. Whatever the data you have taken, whatever the features are that you have taken, maybe not that much useful to predict the output. Whatever the features you have taken, features means what? Columns. Whatever the column that you have taken may not be exact features or required features in order to predict that output. Let's say you are predicting whether that particular case is benign or malignant. Benign or malignant. In that case, you need specific features. Specific feature you need. If you are taking features that are not useful to predict the cases, whether it is benign or malignant, in that case, you won't be getting maximum good accuracy, of course, right? So in that case, what you have to do? You have to go to the data frame again. You have to research on that, and whichever the best features, then you have to add those features into your data frame. Then again, you have to train your data machine learning, and you have to do prediction. When you have underfitting case, you have to look into your data frame and do some feature engineering, or you have to add some features which are necessary to predict the output. Yeah. When it comes to regression, yeah, what is overfitting when it comes to regression? It is called a regression line. Whenever best fit, if we are not having overfitting, we are not having underfitting, in that case, it will be called as a best fitting. In that case, what will be your accuracy? The range will be, I mean, it won't be more than 1 or 1.2 or something 2. Not even 2, just 1%. It shouldn't be more than 1% difference in between training accuracy and testing accuracy. If you have, let's say, if you have 95% accuracy in training, you should be having near to 94% of testing accuracy. Then only we can say it is a best fit. Best fit. If you are having 95% accuracy and you have just 80% test accuracy, it is also considered as overfitting. Overfitting. So you should be very careful about it. You are getting 95% accuracy on training data, and you are getting 60% on testing data. You don't think, yeah, my model is performing really good on training data, I can go ahead with deployment or something like that. It is overfitting. Whatever the thing that learning, I mean, whatever the pattern that learning, machine learning, but it is not performing the same when it comes to testing data. So don't go for deployment or something like that. You have to look into the data frame, or you have to do some regularization, use regularization technique, or do some hyperparameter tunings to bring out the good accuracy in testing. Yeah. What if training accuracy is 90% and testing accuracy is 95%? See, you have limited. It is also comes under overfitting one. See, when you have just the data itself giving the 90% accuracy, how can test will give you that much accuracy? It shouldn't be more than 1% difference. You should be looking into that. Then only it will be called as a best fit. So this is a normal. This is a base model. You can say it is a base model. See, whenever you are, it is a regression line. Whenever you have something data, something like that, what we will do in regression, we have to decrease the error rate as much as we can. So what happens in regression, you will be drawing so many lines. These are so many lines, so that we can decrease the error rate. These are the error rate. you can say it is mean, and we have to calculate distance between all those points. Whatever the points difference will be having in between this, it is called as error rate. We'll be calculating and summing all this. All this difference will be summing. That is only error rate. So what we'll do, the regression line, whatever the regression line we are drawing, we should decrease the error. That is why we'll be one regression line will be drawn. We should decrease the error. But normally we won't be decreasing all. You won't be decreasing error rate is equal to 0. It is not possible. But we will try to minimize that error. In that case, you can do some regularization or you can do some hyperparameters. In that case, you can tune your model. Whatever the model you are building, you can tune it. In that case, you can create a fit, best fit. But your model going through each and everything. Let's say these are your data points. If you are building a model and you have taken one regression line and you have done some hyperparameter tuning, you can simply some curve. I mean, similar to that pattern you might get. That is called best fit. But when it comes to this, it will going through all the points. It is going through all the points. See, it is not predicting. It is simply copy pasting. It is going through each and every point. In that case, it has learned the pattern. Whatever the pattern you have in training, it is simply learn the pattern and it is just copy pasting, you can say. It is not learn anything. It is just copied the pattern and it is pasting. In that case, what it is called? Overfitting. Machine learning didn't learn anything. Just take an example. I have given you 100 questions. I have given you 100 questions. If I give you the same question with same MCQs, would you get high marks? The same in 100 questions, I've given you 10 questions, and you'll be getting high score, right? Of course, you'll be getting 10 out of 10 if there is the same options. But if I've given you 100 questions, and I've given you 10 questions, completely different, nothing to do with these questions. In that case, you'll be getting some accuracy. So in this case, you are not understanding the concept. Whatever the subject that I am teaching, you are not understanding the concept. You are simply marking. What it is called? Data marker, something like. You are simply copy pasting it. You are not learning anything. You are simply copy pasting it. Whatever the option you have, just A option, simply A. In that case, you might be getting 100%. But when I have given 100 questions. For testing, I have given completely different questions. In that case, if you have learned the concept, in that case, you might be getting good 9 out of 10 also you will be getting. But in machine learning, we won't be getting 100%. We'll be getting near to 99, 98% also you might get. In that case, you have learned that concept. You are not copy pasting it. The same case, if you are copy pasting as it is, in that case, what happens? It is simply copying all the inputs, whatever the training data that we have given. It is simply copy pasting. It is not learning anything. So it is not the good fit. So it is a good fit. In the same case, it is in the regression in case of classification. It is a line that we have drawn using the classification algorithm. Then you can do some hyperparameter tunings and you can bring to something like that. It can be called as a best fit. But if it is going through each and every point, see, the model is going through each and every point. In that case, it is overfitting. It is simply learn the inputs or input patterns. It has learned the input pattern and it is simply copy pasting. So it is not a good fit. It is also overfitting. It is a best fit. It is underfitting. And we have ROC curve and AAC curve also in order to calculate the or evaluate the model of classification. We'll be having the ROC and AC, area under the curve. Receiver operating curve. It is a receiver operating curve. It is area under the curve. In that case, what happens? We'll be taking true positives on y-axis and false positive in x-axis, and we'll be trying to predict the accuracy. When you have curve something like that, you can say it is the best fit. It is additionally we can go for ROC or AEC curve. Receiver operating curve, area under the curve. So these are the metrics that we will be using for evaluating the classification case or evaluating the regression case. Same, what is the overfitting? We will be having less accuracy, overfitting, high accuracy in training and less accuracy in testing. It is called overfitting. When it comes to underfitting, then training itself having the low accuracy and the testing also will be having anyway less accuracy. In that case, it is called as a underfitting. So yeah, this is all about today's class, guys. I hope you guys learned something. In the next class, we will be discussing about how we will be doing the pre-processing when you have a data set, how we gonna clean the data. And then we will be seeing some use cases when it comes to, I've told you earlier, we'll be having adipose tissue. How we'll be predicting the adipose tissue of that particular person based on the circumference. We'll be seeing that. And yeah, that is it for today, guys. I hope you guys learned something, and we'll see you in the next class, and have a nice day.